Hello everybody, this is Dr. Christopher White, and in this presentation we're going to spend some time thinking about the collection of data and its interpretation by geologists. So this is going to correspond to section 2.7 of your textbook. So we're going to start by thinking about the Yellowstone area. Now, as I'm sure you know, the Yellowstone area is an area which is geologically active. So we have geysers in that area, so we have places where hydrothermal water is essentially being forced out onto the surface of the earth. And we also know the Yellowstone area is volcanically active. We can see that there are relatively recent lava flows in that area which show us that lavas have been erupted onto the surface of the earth. Now, the thing is when we look at the Yellowstone area and the area that surrounds it, what we can see is that there is a chain of volcanic deposits which stretches along this trend here, marked out by the red line. And so what we can see when we look at this trend is we can see that the ages of these rocks, these volcanic rocks which have been deposited, get younger as we move to the northeast and get older as we move to the southwest. So what we can see is that we've clearly got some kind of geologic process which is depositing volcanic rocks along this trend over an extended period of time. And so there's a couple of possibilities that could explain what we're looking at. So the first possibility is maybe the volcano itself is moving over time. So the volcano 15 million years ago would have been located here, and slowly over time the volcano, or the volcanic area should I say, has been steadily migrating up to the northeast. The other option is that the volcano is actually stationary, so the volcano never moves, but over time the crust over the magma source, which is feeding the volcano, has moved. And so this would mean that this area of crust over here would actually have been here 15 million years ago. And over the last 15 million years, that piece of crust has slowly been moving to the southwest, away from where the magma is sourced from. So these are the two ways in which we can interpret this data. And so as geologists, we then have to say, right, well, what's the most reasonable explanation for this? And in a lot of instances, we will have to bring data in from other disciplines to explain what we're seeing. And so we know that the data that we're looking at here is actually the result of the crust moving over what's referred to as a hotspot. So a hotspot is where we have a big ball of magma that gets stuck at the base of the Earth's crust. And this big ball of magma is stationary. It doesn't move. But the crust, so the surface of the Earth, is in motion. So while the big ball of magma that feeds the volcanoes here isn't moving, the crust that's going over the top of it is actively in motion. And so you can get a volcanic eruption occurring here, and over 15 million years, the movement of the crust is going to take the volcanic rocks that were initially erupted here, and it's going to move them to the southwest. And we can see this, and we know this is happening because when we look at other parts of the world, we can see the movement of the tectonic plates. We can take measurements using satellites, and we can actually see how quickly tectonic plates are moving towards and away from each other, and in which direction they're moving. And so once we have that information, all of a sudden, this trend that we see here becomes quite easily explained. So let's also start to think about what we're seeing in the Yellowstone area at the moment. So we know that the Yellowstone area is volcanically active. We know there are relatively recent volcanic deposits at the surface, and so we know that there's a good chance that the area will be volcanically active again. So if we look at this diagram here, what can we see? Well, this is actually a picture of the Yellowstone area. Please note that north is actually off to the left of the image here. So it's been rotated through 90 degrees. So the orientation isn't quite what you would expect. So what we can see is that there are some areas of the Yellowstone National Park which we can see are actively rising. So we can see the ground there is on the way up. However, there are other areas of the Yellowstone National Park where we can see that areas are actively being flooded. And so we have to think to ourselves, well, hold on a minute, why are some areas going up and some areas going down? Well, it all goes back to the idea of the Yellowstone National Park being volcanically active. So every volcano or group of volcanoes will be fed from a body of magma underground, which is called a magma chamber. And the magma chamber will obviously get smaller as magma is lost and erupted onto the surface of the Earth, and it will get larger when new magma is added to it. So it's just like a balloon. When you blow air into the balloon gets larger. When you let some of the air out, the balloon gets smaller. And so when you have a large volcanic eruption, what you are essentially seeing is magma leaving the magma chamber and being erupted onto the surface of the Earth. This means your magma chamber is going to start getting smaller. And as the magma chamber gets smaller, its volume is going to decrease, and that means the crust, which is above the magma chamber, is going to start sinking down. However, when your magma chamber starts to fill back up with magma, its volume is going to start increasing again, just like adding air to the balloon. And so as the magma chamber starts to get larger, the crust, which is located directly above the magma chamber, is going to start being pushed up and out. And so this upward movement on the northern edge of the lake here is probably the result of a magma chamber underneath it filling with fresh magma. And as the magma chamber is getting larger, it's pushing the crust up and forcing the ground level to rise. Now, the problem is, as this side of the lake, as the northern side of the lake starts getting pushed up, the rocks which were covered by water are now finding themselves being pushed above the water level. And this means the water that was on top of them has to go somewhere. So it's got to flow into the lake, and it's going to start flowing in the opposite direction. So it's going to start flowing to the south. So think of this as being like a seesaw. As one end starts to rise up, the other end naturally has to go down. And so we can see this decrease in elevation being reflected in the fact that these areas are now being inundated by the lake. So as this area starts to go down, so as water starts to move off the rising land over here into the lake, it forces up the lake level and it starts to cover the land to the south of the lake. And so we can see this in the form of areas being flooded, and we can see that trees which are essentially along the lake edge are slowly being inundated as the lake shifts position, as the magma chamber starts to fill up. And so once again, this is just a basic set of interpretations using relatively simple geologic reasoning. And this is what a geologist is aiming for. So we'll collect our data, but then we have to explain why we are seeing what we are seeing. And this is obviously where things can get a bit complicated, because there are lots and lots of instances where you can use multiple explanations to explain the same event. And especially in geology, when you're working over timescales of millions of years, that makes it even more complicated. So you have to accept that in geology, there's not always a nice, simple explanation to everything you observe, but a lot of the time we can come to a consensus about what we're actually seeing. So let's look at another example where we have somebody taking the data and coming up with hypothesizing a model to try and explain what we see. So when we look at the fossils that we find in areas of Africa and South America, we note that those fossils are the same organism, and these organisms are dating to a time period during the late Paleozoic to early Mesozoic. Okay, so what we'll notice is we have the same animals occurring in South America and Africa. Now, if you assume that the continents are not moving, you have to come up with an explanation that can explain how you can have the same animal living on two continents which are separated by a blooming massive body of water. So how can you do that? Well, the most obvious explanation is, right, they've clearly got to migrate. And so you think, okay, well, they start off in South America and they're going to migrate to Africa. Well, there's a slight problem. think about how this would work. You start in South America, so you're going from the, let's say, maybe the grasslands of South America into the rainforests of northern South America and Central America. Then you come into the scrubby grasslands of southern North America. Then you move into the Great Plain environment. Then you move into the boreal forests of Canada. Then you move into the, the ice fields of Alaska, the Bering Strait and Russia. Then you move through the desert environments of the Central Asian plains. Then you move into the mountainous Himalayan environments of the Tibetan Plateau. Then you move into the desert environments of the Middle East. Then you move into the desert environments of North Africa. Then you move into the more warm and wet subtropical environments of Central Africa. And so your organism is going to have to move through a lot of very different environments. And that's not going to work for most organisms. Most organisms are designed for their particular environmental niche. And so, if I was to take a fish and I took it out of water, well, that fish is going to die because it's not designed to live on dry land. So the same goes for most animals. Most animals cannot go from, let's say, a rainforest environment and suddenly be able to migrate happily through, a frozen winter environment. It's just not going to work for them. They're not designed for it. And so in order for an animal to move through that environment, it's going to have to adapt and evolve to be able to move through those environments. And so this would mean that an animal that left South America to migrate to Africa would have to evolve to deal with numerous different environments as it progressed. And this means the animal that would arrive in Africa would be completely different to the animal that left South America. So you would have several different generations would have passed during that time period. Evolution would have taken place, and so the animal that arrived in Africa would not be the same species that left South America. And so we have ourselves a bit of a problem. A large-scale migration doesn't really work. So you have to think, well, can I come up with another way which would allow the same organism to live in both South America and Africa simultaneously? And the answer is, of course you can. You stick a land bridge between the two of them. So essentially you build a bridge made of land and the animals can quite happily migrate from South America to Africa. Done. Well, it's a great idea, but unfortunately there is absolutely zero evidence for this. So this is an example where someone has taken the data, they've taken the data that says, right, we have the same organisms existing at the same time in these two separate continents, how can we explain this? And so they've gone, right, well, a land bridge between the two, that would allow the animals to migrate from one continent to another, job done. Of course, the problem is that when we look at the seafloor between South America and Africa, there is no indication of a land bridge like this ever having existed. And then we have the evidence from plate tectonics. And what plate tectonics actually shows us is that over time, the South Atlantic has steadily been getting larger. So Africa and South America are steadily moving away from each other. So if you reverse that process and start to subtract away the South Atlantic, what you're going to see over time is South America and Africa are steadily going to move towards each other, and eventually they're going to be in direct contact with each other. So they would have been part of the same landmass. And so if they're part of the same landmass, well, then all of a sudden you can have animals migrating from what is modern day South America into modern-day Africa because these two pieces of continental crust are attached to each other and they're moving as one unit, so migrating from one to another is super easy. And so this is an example of where someone has produced a hypothesis based on data that they've got, but unfortunately that hypothesis has been proven incorrect. So you always need to question the hypotheses which are being put forward by people. Do they have the data to support their idea, and is there other data out there which contradicts it? So now let's take a second and we're going to think about this impact crater here. So this is Meteorite Crater, and we can quite clearly see that what we have is a great big hole in the ground. Now, the name of the crater is Meteorite Crater, so you can probably guess what formed it. However, let's go at this from a scientific point of view, and we're going to try and work out how this formed. So we're going to imagine that we didn't know that this was a meteorite crater. So the first thing you'll notice is that the area surrounding it is nice and flat. So from a geologic point of view, it's clearly not a particularly exciting area. There's not much going on which would suggest we have, large movements in the Earth's crust. There are no signs of large-scale volcanic eruptions or anything like that. So it would seem that geologically, this area is on the whole quite dull. So we need to come up with an explanation that's going to explain what we're looking at here. So what do we have? Well, we have a circular feature, a circular depression on the surface of the Earth, and we can quite clearly see that the rim of this depression is raised up relative to the surrounding area. So we need to come up with a model that explains these features. Also, when we look at the rocks along the side of the crater, what we can see is that these rocks are in an extremely bad way. They've been broken up. Whatever has damaged them has clearly done so in a very violent fashion. So we have lots of chunks of rock, all very angular. It literally looks like the rock has been pummeled. Something very big and very powerful has clearly occurred to do this. So when we look at it from a geologic point of view, what do we see? Well, we can see that the area surrounding our impact crater is, geologically speaking, a bit on the unexciting side. We have nice horizontally bedded layers of rock. There's nothing particularly amazing going on there. Then all of a sudden we come to our impact crater and we notice there's obviously, here's our depression, but we can see that all of a sudden this layer of grey rock that was nice and consistent all of a sudden balloons out. It suddenly gets a lot wider right here. We can also see that these layers of sedimentary rock as we approach the edge start to be pushed upwards. You can see it quite nicely here with this layer. You can see we're coming along quite happily, then all of a sudden the layers start to go near vertical. So there's clearly some event taking place which is causing this grey layer to bulge out and this pink layer and this yellow layer to be pushed back. Once again, it would suggest maybe some kind of violent event is taking place. So we need to come up with some models to explain what we're seeing. So these are the models which we could possibly use to explain what we're looking at. So the three models are a volcanic explanation, a salt explanation, or a meteorite explanation. So let's think about what these different models would produce. So let's think about a volcanic explanation. Well, it would produce an explosive event, wouldn't it? A very large volcanic eruption would go, in some cases they can go bang in a really big way, and that might explain the crater. Also, a violent volcanic eruption would be sufficient to cause the rock to fracture and brecciate like we can see right here. So, okay, this seems like an explanation that could possibly work. The problem is that there are no lava flows in our crater, in our depression. If you have a volcanic eruption, you would expect some lava, wouldn't you? We don't have that. And we also don't have any indications of there being a conduit underneath our crater which could bring the magma towards the surface. So unfortunately, although it would seem like it could possibly explain what we're seeing, it doesn't quite work. We don't have all the evidence that we would want to back it up. Okay, so what about the idea of a rising salt body? So salt, although it appears solid, can actually flow like a liquid if you put it under enough pressure. So if you imagine this layer of salt here, which we can see as white, is being pushed down on by these layers of rock directly above it. And so this is a lot of weight pushing down on our layer of salt. And so our layer of salt will actually flow in response to this pressure. And if the layer of salt can find some kind of weakness, the layer of salt will actually start to force its way along this weakness and it will start to rise up. This is referred to as a salt diapir, or sometimes called a salt dome. And so what we can see here is, in this instance, the rocks either side are pushing down this layer of salt, and there's some kind of weakness that we can see here. and this has pushed the salt vertically. Now initially this is going to cause the ground to start to dome upwards. Okay, if you want to see what one of these domes would look like, go on Google Earth and look at the coastline of Texas and Louisiana, and you're going to see along the seafloor of the Gulf of Mexico, relatively close to the coast, you're going to see lots of circular features on the seafloor. And these are areas where a layer of salt called the Luan salt is being squeezed upwards due to the weight of the rocks above it, and it's causing these domes on the seafloor, which is where the salt is being forced upwards along weaknesses. And so initially we would have seen the crust doming up. Well, that helps to explain why we can see the crust being bent back right here, doesn't it? Because if you imagine this area starts getting pushed up, well, this layer of rock would start to go up, it would come down, and then it would come over again. So that would explain why we're seeing these layers of rock being pushed back. Okay, looking good so far. Over time, what would happen though is that through natural processes like rain, the salt would dissolve. And as the salt dissolves, it would cause the dome to collapse, and it would end up eventually leading to the formation of a depression. So, all right, things are looking like we might have a good explanation here. However, unfortunately, no. Once again, although it kind of fits what we see, it doesn't quite get it right. So our first problem is that when we look at our crater, there's no evidence of salt actually in the crater or underneath the crater. So that pretty much, gets that idea killed off straight away. There's also the problem that a lot of the rock that was being pushed up as the salt was rising, well, that rock would have dropped down into the crater as the salt was steadily dissolved away, normally by water. And so this would mean that a lot of the material that was above the crater would actually fall back down into the crater, filling it in. And we don't really see that. So we have ourselves another problem. So okay, so what about option number 3? What about a meteorite impact? Right, well, this one is probably going to fit all of our criteria. So when a meteorite impact occurs, it's going to obviously produce a bowl-shaped feature on the surface of the Earth. It's going to produce a crater. The force of the impact is going to cause the rocks along the edge here to be pushed back. Okay, that also matches what we see. The violence of the impact is going to cause the rocks which are struck to be fractured very, very badly. Remember, this is a really high energy event. So that's also going to explain why we can see all of these fractured rocks in the surrounding area. It also helps to explain how the crater is not full of material, because remember, when the crater forms, all of the material that was in the crater gets blasted out in the form of something which we refer to as ejecta. So it gets ejected from the crater, and all this material gets thrown over the surrounding area. So all of a sudden you can see this meteorite impact model helps to explain what we're looking at. But now we need to just, explain the final feature. And the final feature is this: why does this grey layer suddenly bulge out? Because remember, the thickness is consistent, then all of a sudden it gets noticeably larger. How do we explain this? Well, we can actually explain this by thinking of the crust as a fluid. So if we look at these two diagrams here, or pictures here, what can we see? Well, in this instance, we have some milk, and into this milk, someone is dropping a drop of blue dye. And so what you're noticing is the blue dye is making an impact, so it's hitting the water, it's causing the center to bounce back up, which is what we can see here, and here is our circular depression. You'll notice, though, you can see that the process is producing these raised areas, which we see as ripples. Now, if we look at this drop of water here hitting this water in the glass, we can see here's our crater, right there. And if you look very carefully, you can see that the water line is actually coming up and coming round right there. You can see how the force of the impact is taking the water here, and it's actually pushing it upwards. It's causing it to bulge up because the water is obviously behaving as a fluid. Now, if you imagine the crust behaved in the same way during this very violent, very high energy event, well, the impact itself would smash into the crust and it would cause the rocks here and here to bulge up, just like we can see with this impact crater in this water right here. And so, that's a pretty convincing argument. Now, the final thing that we're going to want to see is we're going to want to see other examples of this which matches our model, because remember, it's always good to constantly test your hypothesis. So what we're going to want to do is we're going to want to find other craters created by meteorite impacts, and we're going to want to see the same features. So here's a lovely example of a meteorite impact, and this one's actually on the moon. So what we can see here is we can see our impact crater quite clearly right there, and you can see that this is the area around the edge of the impact crater. Now normally when you have a big impact, it actually causes the edge of the crater to collapse, and so that's why the edge of the crater looks a little bit uneven in this picture. It's because it's a large impact crater and the margins of it have faulted. Now, what can we see though? So we can see we have our impact crater, but we can see we have this central raised area in the middle. Now, if we look over here, this is the same photograph, but notice that it's the orientation is slightly different. So here's this large impact crater inside it. There it is right there. And here is this smaller impact crater, which is right here. So you can see the orientation is not the same. But what can we see? So we have this raised area right here in the middle. There it is right there. If we go back to our picture of our drop of blue dye hitting our milk, well, there we go. We have this central feature right here. It's sometimes referred to as the center peak. And this is the result of essentially the crust behaving like a fluid. So it's bouncing back up in the middle of the impact, and we can see that right here in this picture. So it's behaving in the same way. If we look at the picture here, once again, we can see this is this stepped rim of our crater where it's gone and collapsed. But once again, we can see it's a raised area which is above the height of the surrounding ground. Same with these raised areas which we can see here and we can see here. So this impact crater is a beautiful example of how the crust has behaved in a fluid-like fashion during the impact event. And so if this model is going to work for this impact crater on the moon, the same basic process is going to work for impact craters on the Earth as well. So we've looked at our evidence, we've tried to come up with a hypothesis, we've come up with a model that we think works, and then to prove our model even further, we've then applied our model to other environments and we've seen the same results. And so this is what a geologist is aiming for. You're looking to produce a model based on the data that you collect, which is defendable and can be applied to other situations, sometimes in different environments. All right, everybody, thank you for watching this presentation and have a good day.